Hi guys, let's go ahead and talk about rational functions some more. I know that so far you have completed two different sets of notes. However, we haven't done any practice. I really like this foldable that you will be completing because it lists all the steps for you in the step format. We are going to start by working out two problems, and then for each of those problems you will see exactly what every one of those steps looks like. So the very first thing that we're talking about is looking for holes. As you can see over to the side, you do have 7 steps whenever you are trying to graph a rational function. The very first step is a look for any holes. Well, holes happen whenever you can simplify a portion of your polynomial. This will give you the x value of the hole, and then you can also go ahead and find the y value. Let's go ahead and see an example. In part A, let's see if my pen will work. Okay. The very first step is to factor each of the polynomials completely. Well, to factor the top one, I do see that I have common 2, and then x squared minus 4. For the denominator, I have a quadratic function, so I might want to ask myself what two numbers multiply together to give me -6 and add together to give me -1. I do believe that those would be x minus 3 times x plus 2. Well, I can still factor the numerator by doing 2 times x squared minus 4 is that difference of squares formula that I have been referring to a whole lot. So we have 2 times x minus 2 times x plus 2 over x minus 3 times x plus 2. Clearly, from the factored form, we can simplify the x plus 2 and x plus 2. However, this right here results in a hole. Okay, we need to find the whole x value simply by taking the canceled out form, x plus 2, and setting it equal to 0. Well, that gives you that x is equal to -2. Whenever x is equal to -2, the function has a hole. It doesn't exist right there on that specific value. Normally we give holes as coordinates, so we also want to find what is the y value. We would evaluate the function at the whole x value, f of -2, and make sure that you evaluate back into this format after you have simplified it. So that gives you 2 times -2 minus 2 over -2 minus 3. I am looking at -8 over -5, which is simply 8/5. Since this here is my y value, let's go ahead and give the whole as a coordinate or as an ordered pair. It is located at -2, 8/5. Please note that holes are very difficult to find on a graph. When we do it by hand, we try to place a nice big empty circle on there. But if you're using Desmos or you're using your graphing calculator, those holes are very difficult to catch. Let's look at example B. For example B, we're going to try the same process. Let's go ahead and factor the quadratic at the top. I need two numbers that multiply together to give me -12 and add to give me +1. I do believe that those two numbers are +4 and -3, and in the denominator we have x plus 3. So here you ask yourself, is there anything that could be simplified? Nope, there isn't. What that should automatically tell you is there are no holes. For our steps 2 through 4, we're going to complete them once again with the same example. the first thing that you want to do is set any non-cancelled factors in the denominator equal to 0 to find any of those vertical asymptotes. For vertical asymptote, 1 is anything in the denominator that was not canceled out, x minus 3 was not canceled out, go ahead and set it equal to 0. Solve, that gives you x is equal to 3. So at the line of x equals to 3, we have a vertical asymptote. The function is going to approach that line, but it will never really cross it. Part 2 is to set any non-cancelled factors in the numerator equal to 0. Take anything at the top and set it equal to 0 to find your zeros. X minus 2 is equal to 0. That gives you x is equal to 2. Please note that this x is equal to 2 is only at the point. The zeros are really your x-intercepts, where x equals to 3 in the vertical asymptote really represents a line going through x equals to 3. And then let's go ahead and find y-intercepts if there are any. To find the y-intercept, we need to calculate what is f of 0. Well, f of 0 is going to be negative 8 over negative 6, which simplifies to 4/3. Let's complete the same steps for example B. It is already in factored form. There was nothing that we could simplify at all. For the vertical asymptote, take your denominator and set it equal to 0. That gives you an asymptote at x equals to negative 3. For your zeros, take anything in the numerator and set it equal to 0. X plus 4 is equal to 0 and x minus 3 is equal to 0. So your 0 happened at x is equal to negative 4 and x is equal to 3. Once again, those here are your x-intercepts. And then we want to find the y-intercept as well. Y-intercept happens at f of 0, and it will be equal to negative 12 over 3, which is equal to negative 4. Let's move on to the next one. For step 5, which is find the horizontal or oblique asymptote. In your notes from last night, you guys saw that it is possible that you don't have a horizontal asymptote and instead you have a slant asymptote, or oblique asymptote is the term that they use. So the very first thing that you need to check is what is the difference of your degrees. Please note that you can only have oblique or horizontal, but you can never have both at the same time. So let's go ahead and look at example A. I am checking for the difference of the degrees. Well, I have a quadratic over a quadratic. Their degrees, the degree of the numerator equals the degree of the denominator. This is the case that we're looking at for part A. In that case, the ratio of leading coefficients is the horizontal asymptote. Since it is a horizontal asymptote, we're going to write that as y equals 2, and then we need to take the coefficients of the leading coefficients of each one of these functions and write their ratio. Well, I have 2 over 1, which is simply equal to 2. And that right here is your horizontal asymptote. Y is equal to 2. That means that your graph is going to approach the line of y equals to 2, but it will never ever cross it. Let's look at the next one. In the next one, we have a second power polynomial over a first power polynomial. Well, for problem B, we are in the third case right here. The degree in the numerator is exactly one more than the degree of the denominator. In that case, we need to divide to find the slant or oblique asymptote, and we don't care about the remainder, we just need to see what is the whole part of that division. We can complete either long division, in which case you would be completing x squared plus x minus 12, and you are dividing it by the denominator of x plus 3. Here, since x plus 3 is a linear function, I'm actually going to go ahead and review synthetic division to show you that division process. I need to write out the coefficients of the quadratic function. They are 1, 1, and negative 12. And I will be dividing by the opposite of plus 3, which is negative 3. For synthetic division, I'm going to bring that 1 over as I see it. 1 times negative 3 is negative 3. 1 plus negative 3 equals negative 2. And then I repeat the process. Negative 3 multiplied by negative 2 is 6. And I add those two together, I get negative 6. But remember what I said, that you don't even care about the remainder? I didn't even need to finish that step. What I do need to know is the full solution, or the whole part of the division. It will always end up being a linear function, and it will be 1x minus 2. So for part B, I do have an asymptote. It will be slant or oblique, and it is at the line of y equals x minus 2. This will be the line that I am going to approach but never really cross. Okay, so last things last. Why did we complete all those steps? So we can go ahead and graph that function. Let's talk about the domain and range of this rational function as well. Please note that you are only given space to graph example A and not both of the functions. When we talk about the domain of this function, well, we cannot have a value at our whole. So in the domain, we cannot have the value of x is equal to negative 2, because this was one of our wholes. And then we also cannot have the value of our vertical asymptote, which happened at 3. Please note, I do not want to see domains written out in this format. You have to get in the habit of writing them in interval format. So we're going to start at negative infinity. We're going to go up to our smaller value, not including that value, and then union from negative 2 to 3, union from 3 to infinity. Okay? In terms of the range, what are the y values that we have to exclude? Well, we definitely cannot have a y value at the horizontal asymptote, so your y value cannot equal 2. But also at negative 2, where we have a whole, we cannot have that value either. That value was 5/8. So to write out the range, our range starts from negative infinity. It goes up to the smaller value, 5/8, union 5/8, up to 2, union 2 to positive infinity. So this right here represents my range. It is always helpful to add some additional points. For those points, we were asked to calculate how much is f of 1. You can always substitute the 1 into your original function. You will end up with a 1. And then if you did f of 4, substitute that 4 in, you should end up with a 4. So let's see how we put all this together. At the point of negative 2, 5/8, negative 2 and 5/8, somewhere around here, I have a whole of my function. At the line of x equals 3, I had a vertical asymptote. So we're going to put a dashed line through it. At the line of y equals 2, we have a horizontal asymptote. We're going to put a dashed line going through it. We can also go ahead and plot the points that we calculated.